Ya, belum lagi.
Belum eh. Cek eh. Cek. Udah ke?
Tak naik lagi.
Sekejap eh. Asal lah.
Okay. It's coming up. Dia lambat sikit. Okay dah. Clear. Alright.
Okay.
Thank you.
So, inilah news on March 8. Daimler considers earlier stop to combustion engines. Daimler ni is a COO for Mercedes-Benz. So it said that combustion engine, they will stop combustion engine earlier than the planned date, which in 2039. So, but Daimler's never said the end date for combustion engines for Mercedes-Benz. So yeah, this is the news. I think that's it.
Okay. Thank you, Farhana.
Thank you.
Thank you.
Macam nak
Okay.
keluar?
Keluar pintu ke keluar ni?
Stop sharing macam mana?
I think you click kat bawah tu. Unshare.
Okay, this one.
Right. Thank you, Farhana.
Thank you, Doctor.
Okay, anyone? Siapa yang supposed to present?
That's me, Irfan.
Yeah, Irfan. Yeah. Irfan.
Yes.
Why you here? I thought you're finishing.
Yes.
Anyway, okay, Tuan.
So this is the news what I want to share today is what is the future of internal combustion engine by Stephen Anderson. In this news, as we know, with the strike emission standard now and the rise of electrical vehicle, it might seem like internal combustion engines become to the end. But Jason Penske believed that internal combustion will live on and continue because he said maybe in the future there are three options to make the ICE more to continue. One option he said to build a homogeneous charge compression ignition HCCI engine. Next option is premix charge compression engine PCCI, and the third one is reactivity control compression ignition RCCI engine. So this alternative ICE engine design may not be ready for now or prime time, but maybe the automaker are looking to build this one for the future. That is that.
Okay, thank you, Irfan. I think the topic that you mentioned just now is the advanced internal combustion engine, which as what Tuan Irfan was mentioning, it's the future. So that's the next content that we should learn in internal combustion engine, but unfortunately, it's not included in our course. But of course, that's something that we can look into. Thank you, and thank you so much, Irfan. Okay, who's next?
May I present, Doctor?
Yes, you may. Thank you.
Okay, can you see my screen?
Yes, it's coming up. Give it a few seconds. Well, it's just blank, Amir.
Okay, sorry. I'll try again.
Yes. Okay. Try again.
share. This is screen 1. Okay, can you see now?
Yes.
Okay,
Yes.
so
Thank you.
Porsche made new pistons that they 3D printed from a very strong aluminum alloy. The newer pistons are 10% lighter than traditional pistons, so they improve the power and the efficiency of the engine. And because they were 3D printed, they could be made into a more complex shape, as we can see in these images. So the mass is removed wherever it is not needed. So the piston is still just as strong while using less material. It also has a better cooling gallery that allows oil flow through the piston to reduce the temperature by 20 degrees Celsius, which is much better than older pistons. And that is it. Thank you.
Thank you very much, Ami. That's very interesting. Thank you. Thank you. Yes. I like that one. Okay, who's next?
May I present that?
Yes. you-
Zulkarnain.
Yes. Yes.
I
Yes, Zulkarnain. Silakan. InsyaAllah.
sharing my screen. You can see the screen.
Can, Zulkarnain.
Okay, so this news about Mercedes. They putting an electric turbocharger. So this technology from Formula One, and they want to bring to the road, which all Mercedes fans can experience this technology. With this technology, there is no turbo lag and improve the horsepower. I think that's all from me.
Okay, Zulkarnain.
Okay,
Thank
that's
you
all
very
from me.
much. Thank you. Yes.
Thank you.
I think half of the Mercedes model nowadays is running on electric turbocharger, right? Okay, thank you, Zulkarnain. Any more?
Yeah. No. That's all.
That's all, eh? Okay. Okay, what about others?
Me, doctor.
Yes, Elizabeth.
Okay, wait.
Okay. Okay, can see.
Okay. So, as we all know that many companies and countries made their decision to ban the ICE vehicles and replace with another technology such as electric vehicles. So, Will Institute, who is responsible regarding to this issue, they are still working to identify the best and suitable policies. This is to ensure that the policies are comprehensive and take into careful consideration as it will affect many factors. So there are three main categories, which is environmental impact, market readiness, and consumer and stakeholder impact. That's it.
Okay, Elizabeth, thank you so much. I think Elizabeth has taken one step further by touching on the policy. Thank you very much, Elizabeth. Okay, Fahim, James.
Yes, sir.
Okay. Do you wanna share your screen?
Yep.
Okay.
I would like to talk about gas engines aren't going anywhere. Despite nowadays many manufacturer and company are paying attention on the electric vehicles, but internal combustion engine vehicles will be around for a long time. This is due to the fact that some vehicles may remain better suit to gas for quite a while. That's it from me. Thank you.
Okay, thank you very much. I think this is from German punya article, is it, James?
Yeah.
Right. Okay, thank you, thank you.
Thank you, sir.
All right, Fahim? Is Fahim around? Okay, nothing from Fahim. Okay, never mind. Let's start. Probably Fahim is slightly late. We can proceed with Fahim later, during our break later. Okay, next, let's move on to our class today. So we've covered chapter. We've already covered chapter 1 and 2. Now, in fact, actually, we are actually moving into chapter 3. So you all can actually you all can download the notes of chapter 3 e-learning as we speak, but you can download later also. But just before we start, I'm actually wanted to show you about your assignment. Can you all see my screen?
Yes, doctor.
Okay, all right. Okay, so I'm gonna hand out this assignment by the end of this session. I'll put it into e-learning. I haven't include in e-learning yet, but just want to show you. This is basically the first assignment they will be doing. Officially starts today and by next week. By the so the deadline be on the 11th of April 2021. Just nice before Ramadan. And this assignment is 10%, okay, 10%. And it only covers from chapter 1 until chapter 3, which is what we're gonna complete today, okay? So this is pretty much, chapter 1 is very straightforward, whereby this is an individual assignment, okay? Individual assignment, so each of you needs to do this. Number 1, illustrate and describe the difference between port fuel injection and direct injection of spark ignition engine. And then question number 2 and 3 is more related to the chapter that we will be covering today. Okay, basically chapter 2, we need to calculate the clearance volume of one cylinder, bore and stroke, average piston speed, and base according to the information that is given. And then chapter 3, based on the given information, you need to calculate the rate of airflow, BSFC, or brake specific fuel consumption, calculate the mass rate of exhaust flow, and also brake output per displacement. So, well, question number 2 and 3 is more on to today's topic. So I'll definitely include this in the e-learning by the time after we finish our session today, so that you can work on it. Okay, so that is basically assignment. That is 10% of your overall marks for this course. So yes, okay. Let's start our session today. Okay, Bismillahirrahmanirrahim. Thank you very much for everyone for your attention and also your attendance. So let's move on into chapter 3. Can you all hear me clearly and see the slide?
Yes, sir.
All right. Thank you.
Yes, sir.
All right. So, chapter 3 mainly consists of engine operations. It is split under chapter 3, it is split into 3 subchapters, which is 3.1 is on engine operating characteristics. Chapter 3.2 is on the engine performances, and in chapter 3.3 is the engine efficiencies. So these 3 chapters, inshallah, we will cover by today. Yes, because chapter 3 is pretty much the basic of on engine operation. Some of the fundamentals we will go through, which also required in the later chapters for you to calculate on other parameters as well. So let's start on chapter 3.1 first, which is engine operating characteristics. Under this subchapter, we will go into cylinder geometry, and we will also go through the engine parameters. Okay. So under cylinder geometry, I'm sure by now you have already familiar with this configuration. It is a 4-cylinder, 4-stroke engine. Basically consists of a piston, and you have the connecting rod attached to a crankshaft. Okay, so this is actually a typical configurations or layout for a 4-stroke 4-cylinder engine. Okay, so picture on the right is a cross section view of a normal engine, 4-cylinder engine. You can see of how the layout of the assembly of the piston, con rod, and also crankshaft. Okay. Okay. So, if you refer back to the picture from the previous slide, which is the piston con rod crankshaft assembly, if you plot it into a 2-dimensional graph, basically it is represented by this typical geometry assembly, which consists of a piston, okay, a con rod, and also the crankshaft. Okay, so of course the piston is located in a cylinder. Okay, so this is basically the basic geometry that we'll be using throughout this course. With regards to the piston cylinder assembly. So capital B is basically for the bore, okay, or in other words, it is the diameter of the cylinder. Okay, S is the stroke, which is the length of where position from of where from the TDC position to the BDC position. S is the piston position. Okay, so in other words, S can vary at any range in between the TDC and also the BDC. R is the connecting rod length. Okay, A is the crank offset. Okay, and degree is the crank angle. Okay, so theta is the crank angle. So theta ni is something that we've gone through on the engine timing last week. So you should be able to imagine the crank degree. Okay, so whenever the point of where the crank offset is at 12 o'clock, it is at 0 degree. Okay, and it's always moving at a clockwise direction. VC is the clearance volume. Okay, so VC is the volume on top of the TDC. So whenever the question or a statement saying that what is the clearance volume, it is the volume of where the piston is at TDC. volume on top of the piston where the piston is at TDC. Displacement volume is the volume, okay, volume of where the piston travels from TDC to BDC. So that is the displacement volume. And TDC, of course, it is the top dead center position, the highest position of the piston, and the crankshaft should be at 0 degree. Okay, if you can imagine that. And BDC is the bottom dead center. Okay, the lowest position of the piston, and by this time the crank angle should be at 180 degrees. Okay, are you clear on this?
Yes,
Okay.
doctor.
Okay, so far so good. So for the next for within this chapter 3, not only on chapter 3 only, but in the following chapters, this you need to understand this. Okay, this one will be the basic for you to do your calculations. Okay, so always keep this figure by your side for you to refer. So let's go on to the engine parameters. Stroke, okay, is a product of 2 times the crank offset. Okay, this is basically, if you have the crank offset, okay, then definitely you should able to know the stroke. Okay, average piston speed is basically the average speed of the piston traveling from TDC to BDC. Okay, of course, the position, the speed of the piston depends on the engine rotation, is RPM, which is why the average piston speed is a product of the 2 times the stroke and times the engine RPM. So the higher the engine RPM, okay, of a given stroke, then your average piston speed would definitely increases. But you need to also remember that the piston speed is not always the same, because as the piston travels up and down, okay, TDC to BDC, because the fact that the transition direction of the piston, there's a transition of direction in terms of the piston. Therefore, whenever the piston reaches at TDC or BDC, okay, the speed will definitely be 0. Okay, but of course, what that is important is basically the average piston speed. Okay, so that is very clear, for you to, the higher the engine RPM, so the average piston speed also increases. Okay, so usually the average piston speed of a normal automotive engine ranges from 5 to 20 meter per second. So it depends, okay. So, but roughly, if you get the idea of, the higher engine, the higher RPM, the higher the engine revs, the higher that does the piston travels. And bore to stroke ratio is another parameter that is very important to determine the engine characteristics. Bore to stroke ratio is basically as simple as the ratio between the bore and also stroke. So small engine is usually ranges from 0.8 to 1.2. If the bore and the stroke is the same, okay, so it means if the bore and the stroke, the length of the bore and the length of the stroke is the same, then that is what we call as a square engine. Okay, of course, if the bore is smaller than the stroke, okay, so that means you have a very tall piston, then is what they call as under square engine. And of course, the over square engine, the most popular ones, bore is always the larger than the stroke. That is just some terms. So next. Next is the distance between the crank axis and also the wrist spin axis can be calculated by using the crank offset, connecting rod length, and also the theta of the crank angle. So the distance between the crank axis and wrist spin varies based on where does the position of the crankshaft. In other words, depending on which at which position of at what, how many degrees does the, where does the crankshaft rotates. So that is the distance between the crank axis and wrist spin axis. Okay, so in other words, this distance from S, from the piston axis to the crank axis, this. Okay. And when S is differentiated with time, the instantaneous piston speed can also be calculated. Okay, so it's basically you can actually determine the instantaneous piston speed by differentiating the distance between the crank axis and wrist spin axis. In other words, differentiation of the S. Okay, you can get the instantaneous piston speed. Ratio of instantaneous piston speed divided by the average speed can be written as, okay, this is basically the ratio of the instantaneous piston speed divided by the average piston speed, which we already have over here. Okay, can be calculated. So in the case of where the question asks you what is the ratio between instantaneous speed and average piston, you can actually use this. Okay, in whereby R is actually a product of connecting rod length divided by the crank offset. Okay, just before we move on, for your information, some of these, I am not saying all, some of the formulas will be given in your exam and also your test. Okay, some of them. There will be a formula sheet given to you. Okay, but I would share you the formula sheet until just before we close to the test. But for now, you just need to understand all the formulas. Okay, so engine displacement volume or swept volume, okay, which is the VD, is the volume displaced by the piston as it travels from BDC to TDC. So in other words, if you minus the volume of where the piston is at TDC from of the volume of where the piston at BDC, then you can have the displacement volume. Okay. Of course, displacement for the engine can be calculated according to the based on the number of cylinder engines, the bore, and also stroke. So this is a very quite common formula which you will be using throughout. Most of the time, the question will ask you to calculate something which requires you to calculate to get the displacement of the engine first, but sometimes the engine displacement is not given. The only parameters that is given is usually the bore, stroke, and also number of engine cylinders only. So if you have the bore, stroke, and also number of engine cylinders, you can always know the displacement of the engine. Then minimum cylinder volume occurs when the piston is at TDC. This is when the piston position is at the highest, and the volume on top of the piston is what they call as the clearance volume, and this clearance volume can be calculated using based on the calculations that you have already calculated of where volume. Yeah, true. Just checking the formula whether it's correct or not. Okay, so clearance volume is definitely when the volume on top of the piston, where the piston is at TDC. So this volume is the clearance volume. Okay. Next is the compression ratio, or sometimes called or with a subscript of C, is defined as volume where the displacement volume divided by the clearance volume. Okay, so that is very clear. If you know the volume of if you know the displacement volume and you know the clearance volume, then definitely you can know what is the compression ratio. Okay, and then you have the cylinder volume at any crank angle. This is basically can actually of any crank given crank angle. Okay, you can actually calculate how much is the volume on top of the piston. So also depends on the crank offset and also the distance between the piston pin and also the crank axis, which is given in this formula. Of course, on, also depending on your bore. This also can be written in a non-dimensional form by dividing it with a clearance volume. So this pretty much of another way is another way of presenting the results. Okay, but most of the time, definitely when they ask for a cylinder volume at a given crank angle, definitely you might need to use this calculation instead of this. Okay, this is just for your information. Okay, the cross-sectional area of a cylinder, this is quite straightforward, or in other words, it is the cross-sectional area of the bore. Okay, this is very fundamental mathematics. Okay, area of the piston, depending on the bore. Okay, so the combustion chamber surface area is the surface area of the combustion chamber, which you can actually calculate based on the area of the piston, area of the chamber, and so forth. This is also can be written as a is another way of calculating the combustion chamber surface. There's two formulas over here, but depends on what information that is available for you to use. Okay, that's pretty much on the basic of the engine operating characteristics. Any questions so far? Okay, good. Let's move on to the so what we've gone through so far in chapter 3.1, which is engine operating characteristics, is just going through some of the formulas that you'll be using in the assignment and also in the later chapters. Okay, so let's move on to the engine performances. Okay, so that now basically you have some understanding on the engine operating characteristics, which is quite useful for you to go use that understanding in to calculate the engine performances. Okay, so we'll go through some of the contents that we'll go through is engine work. Then we'll go through how to calculate your engine torque and power. So let us imagine how the power is transferred during the combustion. So in other words, if you can imagine the fuel that is being injected into the combustion chamber, it is triggered either by auto ignition or the spark plug. So the combustion happens, gas expands, and it pushes down because the expansion of the gas. There's a force acting on the piston to push the piston down from TDC to the BDC during the power stroke. Okay, and that is basically how does the power is being delivered to the piston, to the connecting rod, to the crankshaft, and so forth until it reaches to your wheel. Okay. Okay. So on the combustion chamber work on a piston, work is energy related to the force acting over a distance. In order for work to be relevant, uh, it has to cover certain distance. Okay. So in the case of where in the combustion chamber, piston is pushed into the cylinder, so as it travels from TDC to BDC, the work is done by the system. Okay. Okay. And uh, so this is what they call as the indicated work. Okay, work done on the piston by the gas expansion as a result from the combustion. So this is the initial work uh, that is being produced. Okay, that is being initiated by the combustion. Hence, this is what they call as indicated work. Okay. So if you plot the how much pressure is being produced in a combustion chamber according to the position of the piston, then you will definitely have what they call as a PV diagram. Okay, I'm sure some of you have gone through the thermodynamic subjects and so forth. You're quite familiar with this. In the case, of course, the in the case of where the PV diagram represents all the four-stroke cycle. Okay, so you have the intake stroke, you have the compression stroke, and then you have the power stroke, and then you have the exhaust stroke. Okay, so a PV diagram is very useful to understand how much does the pressure is being delivered to the piston and what is the characteristics or the profile of the pressure throughout the four-stroke cycle. So some of the definitions: indicated work. Okay, this is the initial work. It is the work done by gases on top of the piston in combustion chamber. Okay, it is represented by the area in a PV diagram. So if you plot the pressure, if you can measure and plot the pressure throughout the four-stroke cycle, so the area within the PV diagram, okay, this area is the work. Okay. Gross indicated work or gross work. It is the work done during compression and also expansion stroke. Okay, so it is the work that is within the area underneath during the compression and expansion stroke. And then you have the pumping indicator work. This is the work during the exhaust and intake. This is in the case for natural aspirated engine, it should be negative, okay, because it is working in a vacuum state. Unlike on a supercharged or a turbocharged engine, because the fact that you have a boost pressure to push or to force the air that goes into the combustion chamber. Therefore, because of the boost or because of the pressure, it is the value of the pump of the PV diagram is always in the positive side. So this is basically you have this is the intake and also your exhaust stroke. So for a natural aspirated engine, it is usually below atmospheric, okay? Whereas for a turbocharged or supercharged, this area during the intake and also exhaust stroke will always be above atmospheric. Okay, so in other words, it's always positive in the case for forced induction engines. And the net indicated work, hence the net indicated work is basically a combination of the gross indicated work and also the pumping indicated work. Okay. Of course, there's frictions going on inside the internal combustion engine, and it is basically friction work is basically a loss due to frictions and parasitics, friction losses due to pistons, rods, crankshaft, and so forth. Okay, so like the weight of the piston, like someone presented on the 3D printing pistons and so forth. There, so that is basically having a 3D printing, 3D printed pistons. I would assume it is much more lighter than the conventional casting pistons, so it is probably giving less friction. Okay. So the parasitic losses in a drive, of course, on water pumps, alternators, air conditioners, and camshafts. Those are some of the typical losses. So instead of contributing power to the engine, it's the other way around. It's consuming the power from the engine, or in other words, consuming the indicated power. Yeah. So brake work is the work available at the flywheel after the friction losses. Okay. So if you could compare, just now is the indicator work. It is the work that is being produced inside the combustion chamber, whereas on a brake work is the work available at the flywheel after the friction losses. So friction losses, what are the friction losses? Basically, it's the one that we've highlighted. This one. So you can actually calculate your work brake by by knowing what is the indicated work minus the friction work. Okay. So in other words, brake work is the clean work. Okay, is the clean work after you have the minus the friction work. So in other words, brake work is always lower than the indicator work. So the more friction you have on the engine, the less efficient you have of brake work. The lower brake work you will get at the flywheel. Okay. Let me know. Specific work and specific volume. Basically, it is work per unit mass of gas in cylinder. In other words, it is the work depending on the position of the stroke. Okay, so it varies, and also it is the work that is being produced or available depending on the mass of gas in the cylinder. Okay. So some of the mean effective pressure definition. Mean effective pressure is basically the work divided by the change of volume, or you can it is the brake work divided by the displacement volume, and of course the change of volume can be calculated by understanding what is the volume between from BDC and divided by the volume where the piston is at, TDC. Of course, we already know how to calculate the displacement volume. That so therefore the brake mean effective pressure (BMEP), which is quite common to be used in the later chapters, can be calculated by dividing by the brake work divided by the displacement volume. Okay, and this is the brake mean effective pressure. So in other words, it is the how much. In other words, if I could put it in the layman terms, what based on the total mean effective pressure that is being produced at the indicator at the at within the combustion chamber, how much mean effective pressure would be useful by the time it reaches the flywheel. Okay, so that is basically the brake mean effective pressure. So in other words, it is the effective pressure that is available at the flywheel. Okay. Of course, you have the indicated effective pressure. This is basically the effective pressure that is available inside the combustion chamber. Okay. Pumping mean effective pressure is basically the pumping losses or the pumping work divided by the change of volume. And of course, the friction mean effective pressure is basically the uh, friction work divided by the change of volume. So the concept of mean effective pressure or MEP is the average pressure when exerted over the stroke would produce the same work as the bearing pressure. So for example, BMEP or brake mean effective pressure is a product of when you divide brake work over the cylinder displacement. Okay. So that's just a figure for you to show you what is the pumping work and also the IMAP. So some of the terms that will be used in the later chapters. Of course, you need to understand what is wide open throttle, and also you need to understand what is hard throttle. So wide open throttle, if you can relate, if you're pressing the pedal at 100% position, yeah, so that means you fully press the accelerator pedal so that your throttle body would open at 100% opening. So during this during this stage, the there is very minimum restriction for the air to go in. So all the air will definitely try to rush into the combustion chamber in order for you to and fill up the cylinder volume as much as possible. But you can see that during the intake stroke, okay, so as the piston moves from during the intake stroke, as the piston moves from TDC to the BDC, okay, because the fact that you open your throttle valve at wide open throttle, there's not much of restriction for the air to go into the combustion chamber. Hence, the difference of the pressure from the atmospheric is not much. It's close to each other, which is good. But if you are in a part throttle position of where you probably you are actually halfway pressing your throttle pedal, so it means your throttle body would slightly open, probably let's say 50%, not fully open to 100%. So there's some restriction for the air to go into the combustion chamber. And because of that restriction, there's a huge vacuum create, and which is why you can see that the pressure is way down below from the atmospheric. So this is not good, and the larger this area of B, okay, the larger area of B would definitely include pumping work. Okay, so pumping work is not good, and it will definitely affect your engine performance and so on. So, which is why on part throttle, your engine wouldn't produce so much power, whereas on a wide open throttle, you have a much more better performance. Okay. So, following from the previous definitions, this is just a summary of IMEP, BMEP, and also relationship between engine efficiency and also indicated the usage of mechanical engine efficiency in to understand what is the BMEP. So that is basically some basic relationship. Okay. So typical values. Okay. So spark ignition engines at WOT BMP would range between 850 to 1000 kilopascals. Compression ignition engines at WOT or wide open throttle, okay, is ranges between 700 to 900 kilopascals. For super and turbocharged engines on forced induction engines at WOT, it's definitely above atmospheric, which is 1 to 1.2 or 1000 to 1200 kilopascals. Okay, let's go through on measuring the torque and also power. So torque is actually calculated based on the brake work. So 2 pi torque is equivalent to the brake mean effective pressure times the engine cylinder displacement divided by number of revolution per cycle. So for a 4-stroke cycle, we know that one cycle is one complete cycle is 720 degrees, which is 2 revolutions. So therefore, we use 2, okay, for 4-stroke cycle. Okay, so N is pretty much most of the time is always number 2 over here. So that is how we can get the relationship of how to measure the torque. If we have the brake mean effective pressure and we know the displacement volume, then definitely we could measure the torque. So the higher because on a running operating engine, volume displacement is always the same, but with the variation of BMEP throughout the engine operation, the torque also varies. So in the case of whereby if you want to produce a high torque engine, definitely we need to increase the BMEP and also the engine displacement. Okay, so the higher the engine displacement, okay, assuming that it also produces higher BMEP, definitely the torque is also increases. Okay. Okay, power is basically is a calculation based on how much torque that is being produced and also the engine RPM or engine rotation. So that is basically given by the engine RPM is the capital N. Okay, so 2 pi times the engine RPM times the torque, definitely you can get the power. So there's no way for you to measure power. Okay, the only way for you to calculate the calculate the power is for you to measure the torque first. Okay, so you need to understand, need to measure torque, then use that torque times the engine RPM times pi times 2, then you can get the power in terms of kilowatts. Of course, you can convert to horsepower or whatever units you need to. Of course, you can actually calculate the brake power in terms of pressure by using this formula 1.1 half divided times the number 2, which is two strokes, 2 cycles, or 2 revolutions per cycle, times the mean effective pressure times the area of piston and also the average piston speed. Okay, so there's 2 ways of how it depends on which information which is given. Then using the given information, you can actually measure the power. Okay. So that is basically a typical power. If you can plot across engine RPM, and that is just a typical curve of a power. Well, you're looking at a typical power from a natural aspirated engine, not a turbocharged. And then there is a typical torque curve from a natural aspirated engine. Okay. So you can see that as the engine capacity increases, the torque also increases. Okay, same goes to power also. Okay. So following from definitions, basically you can actually determine what is the brake power based on how much work you can actually determine the brake work depending based on how much work that is being produced inside the combustion chamber, which is the indicated work, divided by the how much work that is consumed by the friction. Okay, of course those are some of the relationship. Okay, units, yes, power would definitely be calculated using kilowatts in this course. But this is just to show what's the relationship, the normal conversion between kilowatt to horsepower. 1 kilowatt is equivalent to roughly about 1.34 horsepower. But in engineering and also in this course, we try to avoid using horsepower. The correct unit for us to use in calculation is always kilowatts. Okay. Some of the power parameters you can actually use. You can actually calculate the specific power. Okay, is how much brake, which is a product of brake work divided by the area of the piston. Output per displacement. Okay, OPD is the brake work divided by the displacement volume. Displacement per unit power is the displacement volume divided by the brake work, depending. Okay, it's just the other way around. Okay, and of course, specific weight is basically the engine weight divided by the brake work. So some of these terms is just for information, might not be relevant in the test or exam. It's good for you to know. Okay. Okay, that's pretty much on chapter 3.2. Any questions so far? We're just going through some of the fundamentals formulas over here, and let me tell you some of the formulas. I'm not telling you everything. Some of the formulas will be given in the formula sheet, but I would share you the formula sheet when I'll share you the formula sheet when the time comes, but definitely not now. Okay, but the formula sheet will be provided in your test and also exam, so it will be much easier for you to refer to lah. Okay, but not all formulas, some of the formulas. Okay, if that do you have any questions so far?
Doctor.
Yeah.
For, I think we all know that brake power is at the flywheel, right? So that means we can calculate it using dyno. Is it true? Or
Sorry.
uh,
Sorry, Daniel, can you speak louder a bit? I think there's something wrong with my speaker.
okay, hello.
Okay.
Okay. So brake work
Uh-huh.
is work available at flywheel. So that means that it is calculated. Can be calculated using dyno, right?
Uh-huh.
Okay. So is there any what can I say?
Is there any
Is there
method?
any way method to calculate work indicated work
Okay. Calculate. Okay.
before
Mm.
apart from using theory?
Okay. Thank you. Yes. The baru nak cakap tadi. There's two ways lah. Sama ada based on theory or calculation. Okay. Or the other way is direct measurement lah. I think what you're asking for is the direct measurement, right?
Yes.
So the correct way is basically what they call as they put a pressure transducer into the combustion chamber to measure the pressure that is being produced during the combustion. So that should be able, and then by measuring the pressure inside the combustion chamber, then you should be able to know to plot the PV diagram in order for you to know what is the indicated work or indicated power. But for you to do that, it's really difficult. It requires a very precision machining and so forth. So that is one thing that is the most challenging. Basically, you need to get a proper machining to to, to locate the pressure transducer into the cylinder head, which is quite difficult. Second, the pressure transducer is a piezoelectric transducers. It's very expensive. You're looking at one transducer, might the cost might the cost will be mostly like in okay, the price of the transducer in Malaysia ringgit probably would cost you dalam 20 to 30,000 for just one transducer. But if you have 4 cylinders, then times 4 lah. That's just transducer.
Mhm.
So yes, and that's the normal way lah for you to measure the indicated power. But people hardly go to that because it's only being done by manufacturers or research centers. It is not being done on a normal basis because it's very expensive, very costly.
So let's say macam kita nak beli kereta baru ke apa, you see the brochure, right? So on the brochure, is it like the brake power or is it the power after transmission losses?
Yeah, true. That's why something you need to ask the salesman back if he knows or if she knows. Most of the time, based on my experience, most of the time they will try to declare whichever value which they think is provides a good value lah to the customers. If they sometimes they state that it is a brake power, for example. Sometimes they don't mention. It's either they mention the brake power or the wheel power. So depends on manufacturers. Some of them they don't declare, or some manufacturers they purposely put it in. They don't publicly spell out it's a wheel or power or the other way around. So it depends. Sometimes, like for example, but manufacturers like Porsche, they tend to publish figures from their flywheel, okay, not wheel. But definitely, all manufacturers they won't declare the indicated power. Definitely, they won't declare the indicated power. They will either declare the wheel power or the brake power. But most manufacturers they declare the wheel power. Most manufacturers, but there's no certain preference. Depends on how they can make use of the figure in their marketing.
And then parasitic losses ni. Is it because of this? Is it because of parasitic losses that most cars right now we have electrical water pumps, electrical water pumps and
Correct. Yeah.
air conditioning, etc.
Yes. Yeah. I think most of the modern cars nowadays, especially I think BMW was the first one started the electric water pump on masses in terms of mass production. I think it's becoming a trend nowadays whereby they don't want to try to reduce the parasitic losses as much as possible, which includes this is not just water pump, including oil pump, alternators, which have most of all the ancillaries which is connected to the crankshaft.
Okay. Yeah, thanks.
Okay, let's break for 10 minutes. Then we continue on the third chapter for this week. So probably we can meet back at 9:20. Okay.
All right. Okay.
All right. See you in a bit. Can you see my slide?
Yes, Doctor.
All right. Let's go through this one very quickly. So next is the engine efficiencies. Continuation from the engine operating characteristics and also the engine performances. So some of the areas that we'll go through in this chapter is air fuel ratio, specific fuel consumption, and also other efficiencies, okay, under the internal combustion engine. So So some very general definition of efficiency in engineering is it is the ratio of the useful work performed by a machine. So in this case, it's the four-stroke cycle or engine uh, in a process to the total energy or heat taken in. Okay, that is the basically general definition of efficiency. So on the air fuel ratio is basically okay. Energy input into engine is from the combustion of hydrocarbon fuel. Okay, most of the time. So air oxygen is needed for react chemically with the fuel to combust. Okay, there must be a portion of oxygen to for the fuel to combust. So with the two elements between the fuel and also the air, hence the air fuel ratio term is actually created, and this is the ratio of how much composition of air and also fuel at, at a given time. Okay, so the air fuel ratio can also be classified as fuel air ratio. Okay, it's the other way around, but most of the time we will be using most of the time, and also for this course we will only use the air fuel ratio. Okay, so what is air fuel ratio? It is the ratio between the mass of air and also the mass of fuel. Okay, or the specific mass of air and also specific mass of fuel. It's just a ratio between the air and fuel, hence come the air fuel ratio. Whereas on the fuel air ratio is the other way around. So it's just the ratio between the mass of air and mass of fuel and also mass of air. So the same goes for the specific mass of fuel over the specific mass of air. Okay. So regardless of whether is it the total mass or the mass flow rate or specific mass, it's just a ratio, and both will definitely produce the same values of air fuel ratio. So air fuel ratio is in air fuel ratio there's a term called stoichiometric. Okay, this is basically stoichiometric is the chemically correct ratio of fuel to air, which will oxidize the fuel completely into water and also CO2. So in the case of where for gasoline cases, okay, for the gasoline to oxidize the fuel completely into water and also CO2, the air fuel ratio is 14.7. Okay, so in other words, the stoichiometric of gasoline is 14.7. But when we change the fuel to diesel, okay, because the composition, the chemical composition of diesel is different, the stoichiometric also changes, 14.5, slightly change. But in the case of whereby totally different composition of fuel from methanol and also methane, the stoichiometric also changes significantly. So most of the time, in our cases, if we are using gasoline, which is quite relevant in most of the mass production nowadays, the stoichiometric should be at 40.7. So in other words, what is the ideal air fuel ratio for gasoline? That would be 14.7. So in other words, what does the 14.7 means? It is for gasoline, the stoichiometric 14 the composition of fuel to air. So that means there's 14.7 parts of air to the ratio of one portion of fuel. Okay, so whereas for diesel there's 14.5 portion of fuel, diesel fuel, compared to one portion of air. So the correct way of writing this is 14.7 to 1, or 14.5 to 1, or 6.4 to 1, or 17.4 to 1. In the methane case, in order to hit the stoichiometric, where most of the most of the methane is converted into water and CO2, you will need 17.4 portion of air to at every one portion of methane. So that is basically the air fuel ratio. Okay. So if you can plot a normal typical engine or normal operation, most of the time, it will go to stoichiometric. Okay, stoichiometric now. In this case, you can see that the x-axis is the engine speed, y is the lambda. Okay, so lambda is another form of AFR. Okay, it's another form of air fuel ratio. So in air fuel ratio, the stoichiometric is 14.7, but lambda, the stoichiometric for lambda is actually at lambda 1. Okay, lambda 1. So lambda 1 is actually air fuel ratio 14.7 for gasoline. So you can see that at most of the time it will try to get the engine will try to combust as much as possible at stoichiometric. But of course, as the engine speed starts to go higher above 3000 RPM, the lambda or the stoichiometric will go lower. Okay, when it goes lower, that means that the fuel portion will becoming more compared to the air. So in other words, the portion of fuel is being increased, okay, over a certain portion of air. So in other words, you're putting more fuel into the engine, and in this case, there's so many reasons why. One of the popular reasons, well, there's two main popular reasons why fuel is being injected at high engine speed. One is because to produce more power. Second is for cooling, because fuel is also and fuel is actually a cooling agent to cool down the combustion. So that is one of the reason why at high engine speed you get more fuel lah, injected. Okay. So if that is basically at given at a certain conditions, okay. But what if in terms of the overall performance of the engine, you can see that the air fuel ratio varies accordingly. So you can see that this is the region whereby this is the x-axis is the engine speed, the y-axis is the BMEP. So as the black thick line over here is where the engine is actually producing at full load capacity. So in other words, that is the maximum engine operation. You can see that as the engine gets closer, as the engine operation gets closer to the full load conditions, it will tend to become lower and lower and lower. Okay, so lower when the air fuel ratio starts to get lower. In other words, your fuel is being is your fuel is increased. Your fuel usage is being increased. As I said, why there's so many reasons. The two among the main reason is basically to get more power and also to acting as a cooling agent to cool down the combustion chamber. So another is the equivalent ratio. Equivalent ratio is actual fuel air ratio to the stoichiometric air fuel ratio. This is something that you can use just to understand if the case of where the question asks you to what is the equivalent ratio, then provided that you know what is the stoichiometric air fuel ratio divided by the actual actual air fuel ratio that is running over, at a particular time. Oh, no? Specific fuel consumption is basically the fuel flow, how much fuel is being used per unit power output. So it is a ratio of how much fuel is being used over power output. Okay, hence the formula is where is a product of mass of fuel mass flow divided by the brake power. Okay. So of course you have the brake specific fuel consumption. Of course you use the brake power. If it's indicated specific fuel consumption, you use the indicated power. So it depends. If most of the time it will ask you what is the brake specific fuel consumption, it is basically asking you how much fuel is being produced over a certain power that is being produced at a specific time. Okay. So that is brake specific fuel consumption and also indicated specific fuel consumption. Okay. Sorry, this one's supposed to be ISFC, not BSFC. So BSFC is the brake specific fuel consumption. This one silap ni. Okay. Mechanical efficiency is the efficiency to translate the mechanical work from the indicated to brake. Okay. So the what is the it is being represent it is basically a ratio it is basically okay, sorry, it is the brake work divided by the indicated work. Okay, so how much work is being produced by the indicated power, and then you compare that with the how much power that is being produced at the flywheel. Okay, if the ideally if there's no friction, if there's no losses, the indicated power, okay, the indicated power would produce the same is the same as the power that is being produced at the flywheel. Then you have the mechanical efficiency to be at 100% or just one. Okay, but in the real case, that's not the that's not what happening in the real life. There's frictions, there's losses, and so forth. So whatever power that is being produced by in the combustion chamber or the indicated power as it travels towards the flywheel, there's so many losses and there's so many friction consumptions and so forth. So the power will tend to reduce. But how much it is being reduced, this is actually being measured as the engine mechanical efficiency. So this is just to show the BSFC across the engine speed. So of course, BSFC varies based on engine operating conditions, engine and also other parameters as well. So in a typical engine, BSFC varies a lot. It doesn't stay at value. Okay, that's the whole idea of this slide. So that shows how much. That's the typical characteristics. This one is just for your awareness. So you can see that again this map shows that how BSSC varies according to engine speed and also engine load. Okay, engine load is being represented by the BMAP. So it's not consistent. It's not constant, but it varies throughout. And this characteristics of BSFC varies between engine. Varies between engine. Doesn't it's not a one rule. It's not there's no certain rule that the BSFC should behave. It varies between engine. Okay. So again, you can see how behavior of the BSFC. This is just to show what's the effect of the higher the engine displacement or engine the higher the engine displacement, by right theoretically the BSFC should be lower. Okay. Okay, this is just a performance curve of engine torque, engine horsepower, and fuel consumption. So combustion efficiency is the efficiency to burn all fuel. So in other words, what the combustion efficiency represents, okay, how effective if you inject 20 grams of fuel, for example, in a certain cycle, would you be able to burn all the 20 grams of fuel? If you manage to burn all the fuel, then you have a combustion efficiency of 100%. Okay, but that's not the case lah. Okay, most of the time it will only reach between 80 to 90%. Okay, there must be some leftovers. Okay, thermal efficiency is the efficiency to convert the heat supplied into work. Okay, in this case, in today's world, I think the highest thermal efficiency for internal combustion engine, I think we're reaching about 50%. Nothing more than that, I think. Correct me later if you have any question, if there's any work or production engines that has reached thermal efficiency above 50%, do share. But as far as I know, as of today, highest thermal efficiency for internal combustion engine only reaches 50%. So thermal efficiency is basically how much work, how much energy is being converted into useful work. Okay. For example, if you are supplying 20 grams of fuel, so there's a certain portion of energy is being included in that fuel. Can all the energy be converted into useful work? Okay. So as of today, only 50%. Okay. Unless in future we don't know. Probably that is getting more efficient lah. This one. Volumetric efficiency is the efficiency to fill in the cylinder with air. So if you have one cylinder, if you have a cylinder with 1 liter volume, if you manage to fill in all the air, if you manage to fill the volume, the 1 liter volume with 1 liter of air, then you should be able to achieve volumetric efficiency. Okay, so most of the time for natural aspirated engine, you probably the highest volumetric efficiency can reach is probably close to 98 to 99%. Okay, but on turbocharged engines, because the fact that you have a compressor to force the air into the cylinder, which is so your volumetric efficiency For turbocharged engine, definitely higher than 100%. You're looking at between 130 to 140% for turbocharged engine. So heat added for one cylinder engine is basically this is some of the heat formulas that is being. I'm sure most of you have already quite familiar with this. This is basically some of the same equations or fundamentals from thermodynamics. I won't go through detail on this. So this just to basically just to recap you lah. Yeah. It's the same thing from thermodynamics and so forth. Okay. Okay. On volumetric efficiency, so it's the measure of air mass entering cylinder during the intake stroke. So typical values for wide open throttle for natural aspirated engine is between 75% to 99%. But again, for turbocharged engine, definitely it's above 100%. Okay, you're talking about NA engines, yes, up to 99 or probably close to 100%, probably. So definitely, because the fact that it's measuring the mass of air entering cylinder during the intake stroke, for you to calculate the volumetric efficiency, you need the mass flow rate of air divided by the air density and also the displacement volume. You want to use the if you want to use the mass flow rate of air, okay, on top of this is basically mass of air. If you want to use the mass flow rate of air, then definitely you need to times 2 divided by the air density times volume displacement times the engine speed. Okay. So that shows the volumetric efficiency curve. Volumetric efficiency is that correlates very well with the torque. Okay, so this is basically, in other words, if you want to get the highest torque, the best for you to do is basically refer to this formula. Okay, how you want to as the volumetric efficiency increases, your torque also increases. And how to increase the torque? You increase the volumetric efficiency. How to increase the volumetric efficiency? You need to consider the mass of air that enters and also engine speed and also volume displacement. Okay. So air density, I won't go through this one. This is basically basic fundamental something. Okay, that's pretty much for chapter 3.3. Any question for today?
Doktor,
Yes.
tadi saya lambat masuk kelas sebab saya
Okay, Fahim. Do you want to present, right?
Yes.
Okay, please do so, Fahim.
Okay. Here I will share my content in 1 minute. Okay, let me just. Are you able to see? Are you guys seeing this? Are you able to see? No.
No.
Okay, let me just. How about this time?
Okay.
Okay. My particular topic is basically Volkswagen has basically stopped their engine development. They are still from this news article. It still says that they are still going to make internal combustion engine. It's just that they are not going to make a new family or a new class of engine. Interestingly, there's also mention about Audi and and Audi also under which is a subsidiary of Volkswagen, also stopping their engine development as well, just as Volkswagen is. So that's pretty much about they are focusing towards the producing more.
They wanna make turn the coin upside down lah, trying to make things right lah. Okay.
Actually, ada satu soalan, one
Yeah.
question.
Yes.
So, you said about if we want to increase torque, we need to increase the volumetric efficiency, right?
Yeah.
So, is this why turbocharged forced induction engines have superiorly higher torque than natural aspirated?
Yeah. Let me show my screen. So, can you see my screen?
Yes,
Dia nampak
Doctor.
screen. Okay. So yeah, if you look at this formula, particular this one, okay. So on turbocharged engine, you have a boost pressure to basically to manipulate how much air is being introduced into the cylinder, which is why you have your torque curve on a turbocharged engine is very squarish. You can hit the maximum torque at probably as early as nowadays you're looking at probably at certain engines. I know EcoBoost engines they can reach to 1000 RPM, highest torque at engine speed of 1000 RPM. How basically the turbocharger is capable to produce so much boost when with higher boost, of course, higher mass airflow goes into the cylinder, and therefore you have a very high volumetric efficiency at a lower engine speed. So this is basically a typical curve that you look at on a natural aspirated engine. All natural aspirated engine will have quite similar profile. You have a very like a dome shape, okay. Whereas on turbocharged engine, it's very squarish. So it means turbocharged engine is able to bring the peak of the volumetric efficiency as early as possible, and probably as early as 1000 RPM. So which is why on the latest today's turbocharged engine is very responsive. You should drive the Pro Activa.
And then bila saya tengok oh sorry, and then when I look up the performance chart, performance graph of turbocharged engine, this one is the one I'm seeing here is EcoBoost punya, and then of course lah CFE, then Activa punya turbo and everything. They all have this same characteristic of the torque plateauing at a certain level. Like why they didn't go, to the moon or something? Why?
Okay. That's because when you are actually boosting your engine, there's a certain design limit that is constraining, so that the combustion pressure doesn't exceed the design limit. So certain engines, which is why on turbocharged engine, they are actually designed for to withstand higher pressures and so forth, which is why on turbocharged engines they have better products, stronger connecting rods, stronger crankshaft and so forth. This is basically to cope with the combustion pressure, which is quite high. Which is why on some engines they are actually designed to only withstand certain pressure. And for example, if the engine is actually they're targeting if it's a 3-cylinder 1.3 liter, let's take the 1.3 or 1.5 liter turbocharged engine, and they are expecting to produce a torque or power that is equivalent to a 2-liter engine. Definitely they need to consider for a better design in terms of strength, in terms of material. But in the case of where they are only trying to compete with probably 1.8 liter, for example, instead of 2 liter. So the design, the engine design wouldn't be so critical compared to higher performance target. So of course, like for example, it depends on what is the target of the engine. If it's a 1 liter turbocharged and they are trying to compete with a 2 liter, definitely the design constraint must be really be stringent and so forth, so that they can actually have a very aggressive performances. But if the 1 liter turbocharged is trying to compete with the 1.3 liter instead of a 2 liter, then definitely the performance, the characteristics of the 1 liter turbo wouldn't be the same lah. Okay, which is why it's quite unfair for you to compare between 1 liter and 1 liter performance. It depends on which design strategy that the manufacturer wanted to take lah. Does that answer your question? Danny?
Yes, sorry. Tak terlupa lah mute. And then lastly, like I found a trend lah in apa ni, in small displacement turbocharged engine is that they have high torque but low power. Let's say the Ativa, I think about 100 something, 150 kot.
Yeah.
Yeah, 150 Newton meters, and then but then the
Okay.
the power is about, I think 100
Mm.
something.
Yeah.
Just 97, sorry, 97
Yep.
horsepower.
Yep.
So yeah, why is that? Like what I meant is like, if we want to compare products, cars, should we look at the torque or the power? Which one of the numbers are relative to the performance?
Okay, if you're going if you're going for our daily usage, definitely the parameter that we should look into is definitely the engine torque, because that is pretty much relevant in our daily usage. When we require that torque during acceleration, during cruising and so forth. So those are the things and those driving conditions require torque instead of power. Power is relevant when we wanted to have we want when we wanted to travel at higher speed, for example. Okay, or for performance competition usage, motorsport usage, then only we should go for power. But again, it depends on our usage. If we're talking about passenger cars, on road passenger cars for daily usage, engine torque is much more important compared to power. So we are pretty much because the fact that when we drive on normal usage, we hardly reach anything above 4,500 RPM. Okay, most of the time when we drive, our engine speed ranges from probably 1,000 RPM to 4,000. Okay, most of the time it will be below 3,000 lah. And because of that, because of the lower engine speed usage, torque is pretty much very important. If I buka balik your torque punya, because torque is all your power curve is always the same. Okay, I just can share the slide. Yeah. So your horse, your power, your power curve is always the same. It's always like that. Okay, why? Because it depends on your engine speed. The higher the engine speed, the higher your horsepower will go, or your power will go. But the torque, no, it depends. Depends on the whether it's a natural aspirated, it depends on whether it's a turbocharged, depends on how well, and there's many factors that is uh, being is required in order to have a certain torque characteristics. But for horsepower, definitely. So in other words, most of the time you are using the engine at below 4,000 RPM pun in our daily life. So below 4,000, most of the time, what is relevant for our daily usage, torque is much more important compared to horsepower. Unlike when you travel at high speed, okay, unlike when the vehicle is being used in competition in motorsports and so forth, most of the time the engine revs above 4,000 RPM. Then horsepower play your brake power or your power is more relevant for their usage lah.
So that
Answer your
means,
question, right?
so that means in higher speed, because of the low horsepower, we cannot reach top speeds, or we cannot accelerate more than if we are in higher speeds, like
Yeah.
higher speed, etc.
But of course, and no one actually reaches 300 kilometer power at 3,000 RPM.
Mm. And then lastly, fuel ratio. Apa ya tadi? Lalu pula. Sekejap. Oh yeah, for air fuel ratio, air fuel ratio. So in this, there's this one graph here that they show. Yeah, this one. For this one, the lambda means that it's 14.7 lah kan, the air fuel ratio for this engine.
Lambda 1.0 is 14.7.
Okay, and then yes, is there we know that there are so-called piggyback ECU, right, that changes the parameters of the sensor so that the ECU will the engine management system will change the air fuel ratio of the car depending on the engine speed and all. Does this really affect the performance of the car, as in terms of torque or power?
Yeah, I think ideally, you, based on you can achieve a better, slightly. I wouldn't say very significant. A slight increase of torque and also power with a slightly richer TFR. So in other words, you can get a slightly increase of torque and power with lower lambda. But how much is the lambda? I think, well, based on my experience, anything lower by 0.9. So that means if you have lambda 1, for example, okay, at 1,500 RPM, okay, for example, if you get the air fuel to be richer to 0.9, you might slightly increase your torque and power, slightly. I'm not saying significantly, slightly. But anything lower than 0.9, there's no more increase.
And then if the lambda is higher, does that mean we use less fuel?
Yes, less fuel, but when you have lesser fuel, Okay, so in other words, your combustion is not perfect.
Which it produces
In
more
which
problems.
some of the fuel wouldn't be burned. So you have a very high pollutants. But that's the same case, same thing juga. If you have too much fuel also. If it's too much fuel, then the combustion also same thing. It cannot burn completely, and you know, there's so many fuel being wasted in the exhaust side.
Okay, thank you, Doctor.
Doctor, I have a question.
Yes, yes.
It's just that I got to know about this about new cars basically, but it's natural aspirated cars especially. I noticed that there is a eco mode, but not an eco mode. Not basically there is a eco sensor that will turn on a green eco light when we like press the pedal at certain time.
Okay.
I was wondering, okay, here is what's interesting. When I get to look where is the sensor is, it turns out it is an oxygen sensor instead of a fuel sensor. I was wondering why would they put an oxygen sensor on the exhaust, and then how is that? They call it as fuel efficient for the vehicle to have that sensor.
Right. Okay, Fahim. I think the Fahim, dengar
Yes.
tak? Fahim?
Yeah.
Okay. Basically, eco driving. This is how they do like this, depending on cars. Okay. One method of eco driving is where they manipulate your transmission strategy. So they don't interfere with the engine. So they just play around with the throttle pedal and also your transmission. So what they did was actually to make your accelerator pedal to be very sluggish, okay, trying to prevent any aggressive acceleration, or they can manipulate the transmission so that it becomes it's the same thing. It's trying to prevent any aggressive maneuvers, aggressive acceleration, aggressive deceleration, and so forth. And that is from one way of how they make eco driving. And they didn't actually, when they did that, they didn't actually affect any engine control or any fueling. That is one. Some manufacturers, they approach eco driving using that technique. The other one, the other manufacturer, instead of looking at the only on the throttle pedal and also the transmission, they also incorporated engine strategy. Okay, now on this second one is probably the one that you are mentioning, whereby you said that you found out that it has something to do with the oxygen sensor, right?
Yes.
So oxygen sensor ni is basically the purpose of oxygen sensor is basically to tell how much of air content in the exhaust. So in other words, it determines how much oxygen in the exhaust side. And the engine management system would able to, by understand the engine management system, would be clever enough to by measuring how much content of oxygen in the exhaust to understand how much air that goes inside the engine on the intake side from there. So from there, in other words, it is oxygen sensor is a sensor, is a closed loop system. It's part of the sensoring for the air fuel ratio. So what the engine management system does is basically to control the stoichiometric to 14.7 or lambda 1.1 as much as possible. But how does the how does the engine management system works. So one of the ways is basically to get how much air, oxygen is being available on the exhaust side. That is one. So which is why your eco driving would probably the system that you are referring by him, which you said they are using the oxygen sensor. So what the vehicle trying to do is try to make sure that at all, not any, at all driving conditions, the AFR is always 40.7 or lambda 1.
Okay, I see. I see. Okay. Understood.
So that means that those eco mode yang kita tekan button tu doesn't really change the fuel ratio just slows down the transmission
well,
and the
yes.
engine
Well,
response.
as I said tadi, what it will do, it will definitely trying to make sure that all driving condition, when you press the eco mode too, if the system of the vehicle that you drive has a strategy to manipulate the engine control under the eco driving, then what it will do, the engine will definitely try to make sure that at all operating conditions that the air fuel ratio is 14.7 or lambda 1. It will definitely not go, it will not try to get the fuel anything lower, to get the air fuel ratio higher. Or in other words, it won't cut down fuel to get the air fuel ratio higher, because 40.7 is the minimum, because anything above 14.7 or anything above lambda 1, so in other words, anything above 14.7, so it means lesser fuel, it won't do that. So 14.7 is the we're talking about gasoline, right? If you're talking about gasoline, 40.7 is the limit. Okay. Again, macam Daniel, as as what you asked earlier, Daniel, what happens if we hit above 14.7? So it means the fuel is lower, yes, but the combustion is not perfect. When the combustion is not perfect, yes, you are consuming lesser fuel, but the amount of pollutants that you are producing is much more higher.
Okay, I see.
And then I also read about there are some pollutants that can poison the catalytic converters. So
Yeah. Yep. True. So but there are studies at the moment. I mean, no one is actually okay. In fact, this is my personal opinion. No one is actually looking into how you want to mitigate if for a linear mixture. No one's actually looking at how we can get the combustion right if we have the AFR above 40.7, which is something that we can look into if you want.
sure, can.
I think just to share, a couple of years ago, I think some of the teams in Prodo Eco Challenge did that in order to get a better mileage. I think that's what they did. Yes, they get a better mileage, but how much emission they produce, that is not being spoken of. You get the mileage with lesser fuel, but again, remember that all of this, like all of the news that you all sharing, about Volkswagen, about Porsche, about Lamborghini, and so forth, whatsoever, they are all being pressured because the fact they are trying to reduce emission, not because they're not saying, oh, you need to get a higher mileage. No, they are saying produce lesser emission. Alternatively, which is the best solution they have right now is, of course, electric vehicle. So of course, internal combustion engine, it's very difficult, which is why they don't want to have a very big headache, resort to electric vehicle.
But then the eco light yang dekat dalam all the produas and everything, that's just for behavior kan the
Yeah, I think most of, okay, it depends on some manufacturers. They want to really put proper development on those eco mode. They will definitely involve the engine control. But for, I know that certain cars, not the expensive one, the low the affordable ones, the affordable vehicles nowadays, they are all they are focusing on the pedal progression and also the transmission strategy to make it very sluggish in order to achieve better fuel consumption. But like I think I've already, but you can actually have your eco driving on. You don't need to have those technologies. You can actually practice those sluggish driving methods. Of course, you definitely will have a better fuel consumption, even though without the eco mode. It's just that you need to drive very smooth, reduce aggressive accelerations and so forth. So, but of course, on those vehicles with eco mode, they are all actually being controlled, and they are actually being manipulated for you.
I wanted to share a little bit about my personal vehicle actually. I gotta say that I think the one that was used in the most produas is the second one that you mentioned, Doctor. They actually manipulate the engine performance, that sort of stuff. Because what I noticed is that when I completely let go of the throttle, the eco sensor actually turns off, and not actually turns off. The light actually turns off, indicating that somehow there's a presence of oxygen on the exhaust side of the engine. But when I press the pedal up to 2000 to 3000 RPM, that usually the sensor will start to the sensor will turn on. And I think what Perodua has is actually what Toyota has. It's just my personal opinion, but I don't know whether it's true or not.
Yeah, I think this it's not a surprise if we have a similar technology between Toyota and also Perodua, because most of Perodua's powertrain they are all actually originated from Toyota. I mean, and we know that some of these technologies are actually quite modern. And I think from Perodua, I would say it's quite modern these days, because they actually originated from Japan. So yeah, I think you'll be surprised of how much technologies has been put in Perodua cars nowadays.
Okay.
Atifa ke Fahim?
Asia.
Oh, Asia.
Asia in 2014, yeah. That was 2014, like 6 years ago.
I actually personally drive a Brezza for daily basis. So,
Okay, guys, I think it's
Okay.
already 10. I don't want to, probably most of you want to early sleep today.
Okay.
Thank you so much to everyone for your participation, your attention, and also your attendance. Thank you so much for your feedback. We'll continue back next week. Please immediately start on your assignment. Everything can be downloaded in e-learning. Okay. In your assignment, if there's any question you want to ask about your assignment, please do email me, because I keep my email very closely to me. Because even in that way, you can actually write a long sentence lah in WhatsApp. In WhatsApp, Well, I prefer email because in WhatsApp, I'm quite lazy to type in WhatsApp sebenarnya. So in emails, okay, because I usually type my emails in keyboard using keyboards. I hate to use my fingers. But then, if you really need to contact me, it doesn't really matter. I prefer emails. Okay. Anything you want to ask about assignment, please do so. Okay. It's an individual submission, but if you want to discuss or do the work together, that is encouraged. Okay. I believe that you all can learn better within groups. So, want to do the assignment together, should be no problem. But the work that you want to submit must be yours. Okay. Okay, everyone. Thank you very much. Don't forget to sign your attendance, and I'll see you all next week. Okay. Have a good night, everyone. Thank you very much. Bye bye. Assalamualaikum warahmatullahi
Thank you,
wabarakatuh.
Zed.
Thank you,
sir.
Doctor.
Okay.
Thank you, Doctor.